Okay, great. So with that, let me go ahead and introduce you. I'm really excited today to have Liquan Pei from TiDB. Liquan is currently a senior database engineer, from PingCap, but presenting today on TiDB plus Pulsar, event streaming architecture in action. So with that, Liquan, I will go ahead and hand it over to you.
Thank you, Caroline, for the introduction. And I'm Li Kuan. I'm currently a senior database engineer at PingCap. And before I working at PingCap, I have been working at Pinterest as Confluent. When I was at Pinterest, I'm mainly working on the streaming infrastructure for the ads at Pinterest. And we actually work very closely with a Kafka team. And we actually definitely share feel the pains of running Kafka, especially at scale. And a lot of times we are kind of like hoping that the Kafka cluster is more stable and don't cause issues for us because we kind of like share the same pain. And then that kind of like, and I think the pains of Kafka makes me like kind of like find the Pulsar, and I read through a few blog posts about Pulsar, and I really liked the architecture. And then I started a little more, and that's why I think today I want to talk more about and how TiDB and Pulsar can work together and to be a kind of very practical event streaming architecture for your company. And here's my contact information. And we are also hiring. If you are interested in TiDB, please apply at our career site. And if you are interested in the opportunity at StreamNative, please also apply there as well. I think that they are doing something really cool, and I do think they have high potential. Okay, so here's today's agenda. I'm first talk about the kind of the rise of the distributed SQL and event streaming. And then I'll talk a little bit more about TiDB itself, quickly go through its community and adoptions. And then I'll talk about some technical part, starting from the architecture side, and also something about the transaction protocol, because it's hard to understand the challenges of change data capture in distributed databases like TiDB without understanding transactions. So I'll spend some time on it, but but I will leave many details alone because it's a kind of complicated topic. And then I will talk about the joint solution of TiDB plus Pulsar. At the end, I'll leave some time for Q&A. So let's get started. I think nowadays, I think the event streaming architecture is becoming popular, and it's very important that it serves as a foundation for event processing and stream processing. At Pinterest, this is kind of a popular architecture. A lot of things are built in with this type of architecture. For example, for the ad indexing, the system monitors changes in certain properties of an ad, advertiser, or ad group. For example, the change of the bid, the change of the budget. And based on that, it will trigger indexing process and recreate a document in the indexing system and for serving those ads. And this is critically important because this reduces the delay of a certain events happens in the database to the secondary downstream systems, and which offers a better user experience. So this has become popular. And at the meantime, there's a rise of the new SQL databases. They are mainly distributed SQL databases. They are designed to be horizontally scalable and fault tolerant. They kind of combine both the nice properties of traditional relational database plus NoSQL. Users can write simple SQL statement and enjoy the support of the transactions, especially the ACID properties. This will make the failure handling from the application side much simpler, and the user do not need to worry about creating their own transaction protocol from the application side by using NoSQL. And with those, I think this two systems, TiDB and Pulsar, are kind of like I think phenomenal systems in this trend. And TiDB is a distributed SQL database. It is inspired by Google Spanner, and it is horizontally scalable, and it is like MySQL compatible. You can use a MySQL driver to connect TiDB. And Pulsar is a distributed messaging system. It has a storage and compute segregation architecture, which is designed to be cloud native. It also offers a multi-tenant architecture and different delivery semantics, which makes it useful to many scenarios. More importantly, because Pulsar has the kind of like computing and storage disaggregation kind of like architecture, it makes the scaling really easy. It definitely solves the pain point of running Kafka in scale. For example, when you want to scale a Kafka cluster, after you add a broker node, you have to move data from the old broker to the new broker in order to scale the traffic. For example, if you want to upgrade your Kafka cluster, you also need to terminate a node and move the data over, and then kind of like and move data back. So this is definitely very challenging. But with Pulsar, this process is very simplified. You can have very fast turnaround time when you scale your node or when you kind of like upgrade your cluster. So before I dive into technical details, I want to talk a little bit more about TiDB, especially in its community and adoption. I will quickly go through it. This is more like marketing material, and you can read through it after you got the slides. So TiDB was started in April 2015, and many people pronounce TiDB as TiDB because it is what it is. But TiDB is actually short for titanium, and we think TiDB is kind of like a kind of resilient, and it can be used by many critical applications. So that's why I call it TiDB. We have global offices. I think today we have more than 370 employees across the globe. And we have offices in Japan, in Singapore, in North America, and in many cities in China. And PingCab is very remote friendly. And since day one, I think our #1 employees was hired because he wanted to work remotely. And starting then, we kind of like build processes, policies to ensure the remote work can be successful. And another interesting fact is that the team is actually also distributed. For example, the transaction team has team members in New Zealand, in Silicon Valley, and many cities in China. Maybe only the team lead will be in the headquarters. All the other members actually in other office locations. And we are now in Series D, and you can see that PingCab has grown fast since its inception. And if you look at the number of stars on GitHub repo, it tends to grow faster compared with MongoDB and CorelDB. And when should you use TiDB? I think you can use TiDB as a way to handle RTP workload at scale. It is really an elastic MySQL because TiDB speaks MySQL wire protocol. You can use MySQL connector to connect to it. And it do horizontal scalability, high availability, and it also offers ACID compliant. TiDB can also be used as HTAP database. HTAP is short for hybrid transactional and analytical database, and which means that TiDB can handle compliance like analytical queries, especially for the real-time queries. Because the way we did is we can have the column store and row store work together, and our column store and row store are strongly consistent. This can be good for aggregations, and so that the analytical queries can run also very fast. But because of today's topic, I will not talk things in detail. If you are interested in how we do the HTAP in TiDB, you can read about our paper last year in VLDB. And it talks about the design decisions and the architectures, and we use to develop the HTAP capability in TiDB. So TiDB has an active community. It has contributors from different type of companies, for example, internet companies and some more like traditional companies and banks. So we have over 1,000 contributors, and we have many special interest groups and work groups to work with the community to kind of improve TiDB, especially the open source distribution. And TiDB has been used by many industries and on many use cases. And it also has been adopted by many companies, for example, Square, Hulu, Dailymotion, and some banks and the payment companies like PayPay. We have now over 1,500 production adopters across the globe. Okay, so I think enough for marketing materials. Now let's switch gear to talk about more the technical part of TiDB. Let's start with the TiDB architecture. Okay, TiDB is really a platform. It has a rich ecosystem around it. And from its core, it has a TiDB database, but it also comes with a set of tools like backup restore, change data capture, data migration, monitoring, and diagnostics. And by the way, all these tools are available as open source. For example, the fast backup restore, which is only probably available as enterprise features for some other distributed databases. But for TiDB, you can get it from the open source kind of like a distribution. Similar for the change data capture. And I think many other databases offer this feature, only offer the basic features for their open source distribution, but many more advanced features are only available as enterprise edition. And you get full features of change data capture in TiDB open source distribution. And TiDB can be deployed on bare metal and Kubernetes. It can also be deployed on different cloud providers with our TiDB operator on Kubernetes. Last year, we offered a managed services. We call it TiDB Cloud, and you can sign up account and then deploy a cluster within a few clicks. It is now in kind of like now in the beta stage, and we'll have a public preview in the coming March, in this March. Okay, so talk about TiDB architecture. So TiDB has mainly three components. One is a computation layer, and we call it the TiDB server. And the second component is storage layer. And we have two types of storage. We have the raw storage, here we call it TiKV, and it's a distributed transactional key value store. And it also has a TiFlash, which is a column storage. And we have placement driver, and the placement driver, it serves as kind of like a cluster manager, as well as a way to allocate the timestamps. Timestamps is very critical for transactions and CDC, and I'll talk about that later. Here, let's maybe zoom in a little bit and look at the TiKV architecture, the storage layer. On top of it, it provides two types of APIs, the KV API and the coprocessor API. Because TiDB is a distributed database, and it can push down some of its computation to the storage layer, and which we use a coprocessor framework to do that. And I'm not going to talk about more about it, because today is mainly about the CDC. And underneath, we have a transactional KV API, and we use multi-version concurrency control to achieve the transactions. And underneath, we have like two kind of like RocksDB. One is for storing the rough logs, and the other is storing the actual data. The data model of TiDB is a sorted key value map, and the key and the data is sorted by the key in the byte order, and key spaces are divided into fixed size chunks, and we call it regions. And from the physical view, and each region has multiple replicas, and we use Raft to ensure strong consistency between those replicas. We actually use a Multiraft architecture because this is a little bit different from many like Raft-based architecture or like etcd. This etcd is single Raft, but the challenge with single Raft, you can only have a kind of like one Raft group, which limits your data scalability. So that's why the things like the system like etcd is more suitable for the metadata, which is kind of like a small volume. Whereas TiDB is designed to handle terabyte or even petabyte scale data, you do need scale. So we use a Multiraft architecture. That is simple. Multiraft means that, remember that we divided TiDB into kind of like regions, and the regions handles each region handles a contiguous range of keys, and we treat each region as a Raft group. Okay, so and in Raft there's one node is chosen as a leader and the other as followers, and because of this, each node, TiDB node, can be a leader for some region and a follower for another region, and the read and the write typically go to the leader of the Raft group. For example, in this case, you have range 4. Suppose that TiDB node 3 is the leader for range 4, then all the read and write goes to range 4. Here's the overview of distributed transactions. As I mentioned before, TiDB is a transactional key value store and expose the full transactional key value API. And the transaction model is based on the Google Percolator with many optimizations to improve performance. It is almost a two-phase decentralized to a two-phase commit algorithm. By decentralized, I mean the transaction state is actually stored in a distributed fashion. It's now there's no central node at the transaction manager as designed in other systems. We use timestamp ordering to handle transactions. The PD, the placement driver, is used to allocate those timestamps. It is a logical timestamp, and we can allocate around 4 million timestamps per second, which means that the timestamp allocation will not be the bottleneck for transaction processing. We support both pessimistic optimistic transactions, and they are compatible. And that is to say, you can have some transactions running as optimistic and some other running at the pessimistic in the same time. In terms of isolation level, we support snapshot isolation and read committed. And the reason we support multiple this tool is that it is commonly used by many databases like MySQL or Oracle, and supporting this to isolation level make the migration easy. Yeah, privacy is just an overview of transaction. Now let's go a little bit deeper and talk a little bit more about the details of how the transaction is handled in TiDB. When talking about transactions, people often think about the ACID, the ACID properties. They are atomic, consistency, isolation, and durability. But in reality, I think two things after the ACID property is very kind of important. The first one is atomicity. And that means when making changes or updates to multiple entities, and those changes will be visible to the external world, either like as a whole or none of them will be exposed to the external world. The second one is isolation. I think the transaction is really, the transaction protocol is aimed to provide a mechanism to execute the transaction concurrently, but also ensure that with the concurrent transactions, the result will be as expected. So that's where the isolation come into play. Isolation means that when transaction starts, which data is available to this transaction, is visible to this transaction, because some data it may already be modified or be accessed by other transactions. You do need to ensure that with concurrent running transactions, you don't violate those kind of like constraints or invariant properties. The transaction in TiDB is a mix. It has 3 key points. It uses timestamp ordering, and second, because TiDB has a distributed architecture, and the data of a single table can be dispersed, can be placed in many TiDB nodes. So when you try to make changes to a single table, even a single table, you kind of like modifying transactions in a distributed system. So every transaction in general in TiDB is a distributed transaction, and that requires a two-phase commit. In terms of like how do we handle conflicts, and how do we use a multi-version concurrency control, and that is kind of like has some nice properties compared with the locking. With the locking transaction protocol, you have to wait, but for multi-version concurrency control, similar to multi-threaded programming, when a read happens, it will not block another read as long as they are, and only when write happens, it blocks some of the reads. So it definitely can have like a better throughput compared with the locking protocol. So let's talk a little bit about timestamps. There are 2 timestamps are important in TiDB. One is the start TS, and the other is the commit TS. Start TS is taken when the transaction begins, and this is important. This ensures that we can get a consistent snapshot for different keys. Okay. And the commit timestamp is also important. This is timestamp that it also ensure that all the entities are a transaction committed, all the entries will have the same timestamp. And for example, when you commit a transaction with timestamp 100, and all the keys this transaction touched will have timestamp 100. And this tells the order of things, what's happening to the external world. And TiDB uses a two-phase commit, right? And there are 2 stages in the two-phase commit. And the first one will be the prewrite stage. And here are the steps. So first we get a start timestamp from PD. So PD ensures that the timestamp allocated or generated is monotonic increasing. And so the start TS will be a monotonic increasing timestamp, similar with the commit timestamp. This is also kind of like a monotonic increasing. I want to say that this is important, and this makes sure that we can order things by the commit timestamp because they are always like increasing. And then we'll build the transactions in TiDB, and after it's done, we'll prewrite the values to the TiDB nodes, and the TiDB will acquire some logs and write the data to TiDB. And then once all the prewrite to TiDB node is successful, it will return success to or failure to TiDB. If all the prewrites are success, and then TiDB means that it can be committed, right? It will send a commit message. And here comes an interesting fact that we can only have one maybe record as our transactional record, because we cannot ensure that everything, all these participants will commit at the same time. So we will choose all the keys touched. We will choose one of them as a primary key, and this primary key will serve as the transaction status. Once a primary key is committed, we'll treat the transaction as committed. And then we can commit the secondary keys like asynchronously. And the reason we do this is that because TiDB needs to handle failures, and the transaction protocol also needs to be resilient to failures. And because modify to one key is atomic, but modify to multiple keys is not atomic, so we cannot like rely on making sure all the participants, the commit of all the participants at the same time. We can only have one key. We can only rely on one key as our transaction status. And here's a kind of visual presentation of what I just talked about. And before a transaction begins, it acquires the start timestamp, and then we may read the data from TiDB, and using start timestamp to get a consistent snapshot of the database. And when we kind of do end, which means that the transaction is ready to commit, then we'll first do prewrite and write all this data to TiDB, and waiting to gather the responses. And once TiDB ensure that all the prewrite are successful, it will commit, and using a primary key as the transaction status, and only wait for the primary key to be committed, and return the success. All the secondary keys are referenced to the primary key during the prewrite. So even if they are not committed, because you can look up the primary key from the secondary key and determine whether this transaction is committed by looking at the primary key, then decide whether we should commit the secondary key or abort the secondary key. So that ensures that the transaction protocols are resilient to node failures, especially the secondary node failures. Yeah, next I'm going to talk about how we encode the data in TiDB, encode the transaction status in TiDB. So I think the idea is simple. We use multi-version concurrency control, which means that we don't only store the current value, but also the history, the previous versions of values. And each value will come with a version. And here we use a commit timestamp as a version. And here's some kind of like how we encode the data in RocksDB, because underlying we use RocksDB to store the data. And RocksDB has a property, has a feature called column family, and different column families shares the same write-ahead log, which means that the operation on different column families for the same will be atomic, and that is critical for to ensure the correctness of the protocol. For example, the prewrite stage will write the default column family and the log column family atomically, and during the commit stage, we need to delete the log CF and modify the write CF atomically. And here let me talk a little bit more about encoding. So first of all, the default column family is save the data. And when we start write the data, or when we do the prewrite, we will write the default family with the default column family with the key and the start timestamp, when with the value is actual value. And the log column family will have the key and the timestamp, and also have the primary key. So, and the log column family used to resolve conflicts, right? If you two transactions are modified the same key, and if they are concurrently modified, one of them will need to abort, or will need to wait depending on whether you're using optimistic transaction protocol or pessimistic transaction protocol. And once you commit to the right protocol, right like column family, and with the commit timestamp and reference to the start timestamp, and with start timestamp you can look up your value, right? And here we have a optimization for like small values, values with length smaller than 64 byte, because if you need to read a value, you need 2 lookups, but for short value, you don't need the second lookup because that is kind of in line with the right column family. Okay, so previously, so I just briefly go through the transaction protocol. There's a lot of things going on. For example, how to handle what are the differences of pessimistic and optimistic transactions, and how do we detect kind of deadlocks in pessimistic transactions, and a lot of things like that, but it's just a very brief overview. And I want to also look the transactions from a different perspective, especially things may be useful for discussing change-state capture. So first of all, I think the commit timestamp can be used to order events, right? Because they are monotonically increasing, and they are also the same for all the keys participating in the transaction. So you, based on that, you can know the ordering of things and reconstruct the transaction. The second thing I think is important to know or to remember is that those transactions in TiDB involves multiple ranges or multiple regions, and these regions can reside in different different TiDB nodes, right? And I think this is important for each node because for each TiDB or for each range, they are rough group, which means that we have rough log, right? And we can, but because we have cross-region transactions, we cannot use rough log only to order things. And the orders need to be determined by the commit timestamp, which means that we do need to reorder things if we need to reconstruct the transaction order. And we need to gather the data from all the nodes of TiDB and reorder. And I think the third things I want to maybe take away is that for the MVCC, we actually store a history of database, not only the current version. I think I want to call this kind of like properties out, because these are kind of important to understanding the change data capture for a database, for also the challenges of change data capture in a distributed database. Now let's move to change data capture. Okay, so what is change data capture? Change data capture is a stream of messages, and each message contains information about data change. For example, if you insert into a user table with these 2 records, and the change data capture will create 2 events. One event with ID 1 and name Liquan, and the second with ID 2 and name Koi. So that is basically, it's kind of it's like a log in the database, right? It's just it just records all these actions happened to the database. And there are a few challenges of CDC in the distributed database. The first one will be gather changes across instance, right? And generating the changes or generating the operations for a single database is simpler in the sense that we do have a Red Hat log or a big, and that is already ordered mostly like the transaction order. But now for distributed database, you actually need to gather and the events from all the instances and reorder them. This is fine, but you also want this to be low latency, because sometimes this is the kind of the purpose of event streaming. You don't want to wait for minutes or hours or to get the kind of event stream if you want the transaction order, right? And also, I think another challenge is that for the distributed database, it cannot be scalable, which means that it can handle like maybe terabyte of data with millions or like TPS per second, which means that the changes generated by those transactions is also can be enormous, right? You do need high throughput and scalable system to be able to gather those data, which means that let me maybe another kind of analogy that you do have a machine that generates a lot of events, and you do need to have a scalable pipe that can also kind of like gather those events and be able to flow them to the downstream systems, right? So the CDC system itself needs to be scaled, right? And the receiver of those events need to be scalable. For example, Kafka or Pulsar, they need to be scalable in order for the end-to-end to work. And also, those need to be highly available, right? Otherwise, the end-to-end doesn't work. So the CDC system itself needs to be highly available. And the fourth thing is important because CDC can also be used as a database backup and recovery. So if you want to support this semantics, you do need to support a sort of like a transactional order, right? And those are the challenges. And here is kind of the architecture for the CDC in TiDB. We call TiDB, and it has a cluster that pulls the changes of data from TiDB, right? And then we have mechanism to assign different changes to different capture nodes in order to achieve a certain transactional order guarantees. And after that, we can also expose the data to different databases like MySQL TiDB or like or system like Pulsar, right? And also there are a lot of details for this system, because I think the major challenge will be reconstruct the transaction orders, right? And now let me talk about a few interesting questions for this system. The first one will be how to emit changes, right? The first one is to get those change data capture, get those events. And I remember that for each row, right, even for each operation, we do have a commit timestamp. For all the operations that is committed, we do have commit timestamp. And we can then emit a change, right, with the commit timestamp. And this is important. And this also solves a lot of problems, because many applications do only require this, for example, notification or even streaming, right? You can use this row order to trigger computations. You don't need to reconstruct the transaction order for these cases. But we do need to sometimes to reconstruct the transactions. And if we do so, we do need so, right? Then we do need to work on and to determine when to expose changes to a downstream, right? For example, if you expose some changes to downstream, for example, if you expose some changes, but you don't know whether those changes will commit or not, that have troubles, because you, for example, you want to support the database recovery and backup case. You kind of corrupt your database because you generate to downstream with uncommitted data. So that is not acceptable. So we do need to know when I can expose certain of data to downstream, because I know that we have seen all the relevant changes for up to a certain timestamp. Then I can clearly I can 100% sure that once I expose this change to downstream, there won't be anything bad happen, like rollback, right? So we achieve this with the concept of resolve timestamps And I think a result timestamp is a guarantee that no previously unseen rows with a lower update timestamp will be emitted. Let's look at example. I think that is important. For example, we have two capture nodes that generate the events. For example, for node A, generate like at commit timestamp T2 with a change of row A to 3. And node B at timestamp T1 is making change of row C to 2. And node A also changing B to 1 at time to 1, right? For example, when the capture node receives this T2 A23, it cannot expose to downstream because it doesn't know whether this transaction is committed. But once it receives the result message or result message that all the from all the node, which means that you won't see any messages lower than T1, right? So which means that you can expose the T1 and B to 1 and T1 C to 2 to the downstream because you know that you won't see anything that will be lower than T1. So I think that's important. The reason we can do this is that all this transaction happens if you commit it, right? As transaction commit, the result timestamp will also be advanced as the transaction commit. You can see that the transaction will advance, and which each advance of a result timestamp, you can expose a few committed transactions to the downstream, so that you can ensure that the changes are kind of like satisfy the transactions. And how to achieve high availability and scalability of TiDB-CDC? In TiDB-CDC, when we partition the work, we ensure that changes for a single table will be assigned to only one capture node. And that is useful to reconstruct the transaction order from a single table transaction. And the way we achieve high availability is to use a PD to maintain the leader or owner of capture node. And one capture node is served as the owner. And the owner is responsible for table scheduling and task dispatching. And also it can handle the capture node failure to redistribute certain kind of like a task to another capture node. And why we use TiDB plus Pulsar? I think I mentioned in the beginning of this talk, I do like the architecture of Pulsar, mainly because of its separation of storage and computation. I think the Berkeley nodes in Pulsar is kind of like stateless, and also it kind of like distribute data into segments, and you don't have the concept of physical partition, and that is nice, right? But that means that when the broker failures, it can parallelly gather the segments from the storage node, and many times this is only need metadata change. So this means that the failure of Pulsar can be much faster compared with Kafka, whereas for failover and scaling, you do need to move data around. So I think that is important because you can see that the TiDB is highly available, and then the TiDB is also highly available, and also Pulsar is highly available, and the end-to-end system is highly available and scalable. And this is make it a good architecture for kind of like working with those change data streams in distributed databases. And this is just the beginning, right? Once you get data in Pulsar, you can use a stream processing framework like Flink to do the processing. And even more interestingly, because Flink data also need to kind of like has a sink to store its result. And because TiDB supports like two-phase commit transactions, and you can achieve like a much better guarantee for writing data to TiDB, right? Like exactly one semantics. Besides, TiDB supports the HTAP capability. It can handle the relatively complex queries like joins and aggregations. And that is also nice because I think stream processing is good for processing computation, which you already know what you want to ask, right? It is good, it provides low latency, but it lacks some kind of like flexibility. If you want to do some like ad hoc like queries, like roll-up aggregations, I think TiDB is a good fit for the event streaming architecture. After you have processed your data, you can write a data TiDB to support more diverse computation. And I think I want to echo that why I think TiDB and Pulsar is good fit, because Pulsar is kind of like a rebalance-free or partition rebalance-free architecture, which enables instant scalability and higher availability, right? And these are very important to make Pulsar to build mission-critical applications. And Pulsar also did a lot of optimization, like zero data copied. So this ensures that the throughput and latency is good using Pulsar, which is also critical for handling event streams at scale. Here are some like real customer stories about TiDB and Pulsar. And this is Zhihu's case, and Zhihu is China's largest Q&A platform. It was using MySQL sharding, and after switching to TiDB, it kind of like reduced the 99 percentile latency. And this data is smaller. Their largest cluster used to be like over 800 terabytes of data. And I think one challenge with MySQL sharding is that you do need to change application code, and which is harder to maintain. And once you shard your database, when you do reshard, it's probably impossible to do the reshard without any downtime. So that's why I think with TiDB, you don't need to do resharding, and there's less code change, and then you don't need to worry about the resharding, the pain of resharding, and the downtime of your application. And Zhihu is also a kind of adopter of Pulsar, and actually Zhihu creates the Pulsar support for TiDCC. And before TiDCC Pulsar, they had some issues with Kafka, especially for the long recovery time for partitions with a huge amount of data, right? That as a design, you need to move data when you do scaling or failover. And then they have big pressure on the brokers with high read and write QPS. And that kind of echoes to the challenge of scaling, right? When you do scaling, the scaling takes time. Even if you detect some high pressure, it takes time to handle those. And also they think Pulsar is kind of designed for their, it's more cloud native, right? It kind of fit their kind of like a future or kind of like a architecture. So I think the reason they choose a TiDB Pulsar is that it support geo replications, support tier storage, is easy to scale out, and also it's kind of a more cloud native architecture compared with Kafka. And I think that's about it. And if you want to try out TiDB, and you can use this one, go to tab, you can probably get the cluster within a minute or so. It's pretty easy to use. And if you want to know more about TiDB, you can read about our AVLDB paper, and also sign up our TiDB Cloud and join our community channels. And that's it. Thank you.
Great. Thank you so much, Liquan, for your time today. And thank you everyone for joining. We do have just a minute or two if anyone has any questions they want to drop in the Q&A. And while we let people do that, Liquan, if you want to go back to slide 47, it might be helpful to actually drop those links into the chat just so anyone can access that directly. And there's just a couple upcoming events I will go ahead and share with everyone as well. One is an upcoming event that we are doing, the Apache Flink and Apache Pulsar communities are doing in the Bay Area. It is a virtual event with Uber and Facebook. So since it's virtual, really anyone can join. I will go ahead and drop that in right now. So that meetup link is for the upcoming event with Uber and Facebook, and that's March 16th and 17th. We also just announced this morning in the Pulsar newsletter that we are doing the first ever Pulsar hackathon. That will be taking place May 6th and 7th. I've just dropped a link in for the Eventbrite there. And one last event, we just launched this last month, and that is the Intro to Apache Pulsar webinar by StreamNative. This was, I think, our most popular event last month. So a great opportunity if you're still learning Pulsar and or if you have colleagues and want them to better understand Pulsar, you can access that there. So lots of links and ways to get engaged, both with TiDB, with PingCap, as well as with Pulsar and with StreamNative. And it looks like we have posted to the panelists.
The panelists, probably you need to...
Yes, thank you so much for that. Okay, so we're going to actually repost those. Liquan, I'll let you do that first.
Yeah, let me do it again. Yeah.
Thank you so much for the heads up there.
Panelists. Yeah, can you see that now?
Yep. Okay, great. And then I'm going to add the link that is for the Bay Area meetup, Pulsar, Flink, Facebook, and Uber will be at that event. And then I'm going to share the link for the upcoming hackathon. And finally, the link for our Apache Pulsar, Intro to Apache Pulsar by StreamNative, which we're hosting later this month. So finally, this will be available on YouTube and on the StreamNative website, as well as access to the slides. So want to thank everyone so much for joining today, especially Liquan. Really appreciate your time in this great presentation, and hope we can all stay connected.
Thank you for the invitation. Yeah.